here. All right,
Awesome.
there we go. And the floor is yours. Welcome.
Brilliant. I will get this shared. Let's see. Give me 1 second to.
Oh yeah. Also, let me check the permissions to make sure you can share. Let me make sure you're a co-host. Okay.
Okay, let me rejoin real quick. I forgot I need to allow Zoom to do this, so I'll rejoin.
Oh yeah.
My bad.
Okay. Yep. Apologies, everyone, for the false start.
Okay, awesome. I seem to have made it back in. Let's see if the screen sharing works correctly. I always love watching PhD students and professors do technical support for themselves during talks. It's one of my favorite pastimes.
Yeah. No, yeah, always assume the first 5 minutes will be tech support, but I hear you loud and clear. I see your slides, so I think we're good.
Awesome. I'll start the video, and I also will put over the chat to the left in case some people don't want to, unmute themselves, instead would like to just chat on the left. I'll leave that open so I can see it, and then I can answer questions if you guys like. So feel free to fill up the chat, and there will be kind of 2 sections for questions. So, feel free to put them there at any time you want, and I'll get to it as we get to it. All right. So let's get started. Thanks so much for the introduction. As you said, I really do love decompilation, and I'm a PhD student in Arizona State. So I'm just psyched to be able to talk on this topic, and I hope you guys get to enjoy some of the things I do, see kind of the past, the present, and where decompilation may be headed in the future. If you guys like to follow along with slides, there's a slide link on the bottom there. You can take it or you can look at it later. It may be useful because I've also filled these slides with some citations in the first half that give you introductions into the state of the art or what's going on right now. So to kind of start this off, I'm Zion, as Dr. Yegman said. I'm Zion. I love decompilation. I'm on Twitter as Mahalos. That's kind of my hacking profile. That's what you'll see me as in CTFs. If you've ever met me at a CTF finals or something like that, I'm Zion, but Mahalos, so 1 and 1, we're the same. I play on Shellfish, as he said. It's a super fun CTF team, which means I love to CTF. Up until just recently, I've been the co-captain, so I do like to see how things move in here and see how research can be integrated into CTFs, because it's kind of a cool way to apply what you've done in binary analysis. And lastly, I'm native Hawaiian, and I'm from the Big Island. We say the Big Island in Hawaii. I know that usually sounds weird because it's like, which island are you from? I'm from the biggest island. I'm from the Big Island. It's the one at the bottom of the chain here. So before I get into this outline of the talk, I want to briefly motivate why you would want to know about decompilation, or why you would even care as to what's going on in this field. So first, what is decompilation? So imagine you have this program, Microsoft Word. I'm sure many of you have Microsoft Word if you're a Windows user. And it's a binary, it's compiled. You don't have the source, and it's not Python, so you can't just open it and read it. But you would like to know what Microsoft Word does. We all implicitly trust Microsoft because they're a huge company, but imagine trying to invest yourself in a new Microsoft Word, a startup's Microsoft Word. How do you validate things they say is happening through your program is actually real? Consider yourself first that you understand how programming works. How can you as a programmer understand how this program works? So ideally, you would not want to be looking at 1s and 0s unless you're a robot. You would want to be looking at source code or something that looks like source code. So we have this nice big arrow here, which encapsulates a lot of things, but it converts this binary stuff into things that look like source. It may not be the original source code, but it looks like it. It gets you something approximated. So why would you want source? Usually the very first thing that people want this source code for is for malware analysis. If you're a security person, you already know malware is a thing, it's a problem, and most malwares are in compiled languages. So whenever you try to analyze them, they're very hard to look at. If it was a Python script again, you could easily debug this and you could see how things are interpreted line after line. But with a big binary blob, you may not be able to even understand where the entry point is. You may not be able to understand how control flow works. So source code kind of gets you to a higher level understanding where you don't have to spend so much time trying to understand what an individual instruction did in this malware, but instead just look at the source. For a lot of us, if you've done a lot of programming in the past, seeing malware in its source form is super obvious. It's not like when you look at assembly. Like if you were to just look at the source code of malware, it's very clear what malware is, right? They're modifying themselves. They're doing stuff with syscalls that they really shouldn't be doing. They're doing all sorts of stuff you never see in a normal program. Another one you might want to do, another manual analysis type of thing, something with humans, is code patching. You find a bug inside of your code and you want to fix it up. You put a Band-Aid over it. It's really hard to do that when you only have assembly. If you've ever played CTFs where you need to patch something, like in DEF CON finals, right? Patching is painful. You need to go all the way to the specific byte you want. If there's a checksum later, you need to make sure the checksum lines up or modify it. It is pretty hard. Now, decompilation enables you to be able to patch things easier. So if we can get perfect decompilation, we can be much, much closer to being able to fix things. This becomes really, really relevant when you have things like old routers or old IoT devices, right? Imagine if you have your nice Alexa in the background. I have an Echo over there that is aging rapidly. You can imagine in the next 3-4 years, Amazon may cut support for this Echo. They may just say, nah, we have new versions, go get a new version. But what happens when I don't have the money to buy a new version and I like my old version and somebody finds a bug online? We are only left with being able to fix it ourselves. And if decompilation isn't available, you can almost guarantee no one will be fixing this for us. So decompilation allows you to independently fix the stuff you already own. This also becomes important for things like military, right? If you've ever heard about military systems, they're usually very old C programs, maybe another language. Sometimes they lose the source and they need to still fix it. And this is where decompilation becomes really important. Another one you might have heard about is bug or vulnerability analysis. For people who are trying to find bugs, decompilers are usually instrumental to being able to identify where bugs can occur. So you have something like Google Chrome, right? Although you can look at the source, which a lot of people do, the source and the assembly may not line up how you think they do. And decompilation kind of discovers those bugs in the middle. So this is helpful for finding normal bugs, but also bugs that may be in the compiler. And lastly is kind of automated analysis. This is the extension that you can do with decompilation. If you have used GitHub a lot, you may be familiar with some of their source checking stuff. They have source code analysis for stuff like dependencies, also for vulnerabilities. They try to scan over some statically available stuff. Now, if you have decompilation, you can accomplish all of these things on a binary because you just take this decompilation, you hope to God it's in valid C form, and then you put it in your automated analysis pipeline. So this is kind of why you would want source for binaries. In all of these situations, they speed up the pipeline or maybe even make things possible. So to scope this talk more, since there is all these different categories we can go with decompilation, we are trying to make decompilation this talk about human-centric decompilation, or decompilation that is helpful for humans to do manual analysis. So you can look at this nice galaxy brain meme going in reverse, right? Starting with full galaxy brain and then down to normal human brain. I'd even argue that last one is tiny brain. But anyway, you can imagine this top one is the cognitive load of analysis. And when you have decompilation, you're trying to move down the galaxy brain to tiny brain so that it's much, much easier to understand it. We can all agree that 15,000 lines of assembly converted to 1,000 lines of source is much easier to understand just because of the quantity. So decompilation really, in this talk, we're targeting making it easier for these humans to understand. So we can kind of drop automated analysis for a little. And on that note, we get to the actual outline of what this talk will be going over, including its technical topics, its background knowledge, and its kind of future views. So first, we'll talk about the origins of decompilation, or at least the origins of most research areas in decompilation. Then we'll go on to the newer research areas, things that people are doing right now and how they've been touched in the past. And I break these down into two different categories called fundamental techniques and auxiliary techniques. The third thing we explore is modern decompilers. We'll talk about kind of the big decompilers you've likely heard of already. And then we'll try to break down who's winning and if we can actually tell who's winning and things like that. I won't spoil that yet because that will be a fun section for section 3. And then lastly will be future techniques. Will be kind of a brief addressing and questioning of the things we discovered in 2 and 3. So let's start with decompilation origins. You may be wondering, where did decompilation really start? If you're naive, you might think it started in the late 2000s, but it didn't. It started in 1994. Some actually argue it started in the 80s because that was the first time people tried to take assembly of things and convert it into C structures. But Cifuentes in 1994 with her dissertation really started it off by introducing these more complex techniques that really acknowledged the compilation process. So 1994, right? We got these programs full of assembly. We disassemble them from their binary form into this nice mnemonic form. So hopefully everyone here already knows how assembly works, registers, memory. I won't even get into different architectures. We'll just kind of assume everything's x86 and it will be okay for now. So you try to disassemble this binary code, this ones and zeros, and you turn it into its mnemonic form. So after you have this mnemonic form, Cifuentes says, okay, hey, we need to actually be able to understand what each of these instructions do more generically. Since if you're familiar with x86, you know there's like, I think 12 different jump variants, and you can do, I think you can do like 15 other ways to do a jump without doing a jump. So, you know, there's a lot of ways to do the same thing. So it's very helpful to lift this into an intermediate representation. You lift it into an intermediate representation, and now you understand how the control flow of the program goes. For instance, this jump not equal would have 2 branches, one being when it's true, one being when it's not equal. You can see that it goes in 2 different directions and then comes back into one, right? So this is kind of the control flow graph, and it gets lifted from these assembly instructions. I'm making a jump here, but this is essentially what Cifuentes did in her dissertation as well, which is this lifting process. Now, to be clear, this also happens in compilers, whether you realize it or not. When you write it in C, the compiler will usually take your C, then turn it into something in the middle between C and assembly that they can do more analysis on faster. For instance, if you use GCC, GCC converts your C into Gimple, and then Gimple into RTL. So there are 2 phases of lifting for GCC. So after she had this control flow graph, right, we still are only looking at assembly. And you may be asking, well, how do we get to linear C statements? This is what I'm here for. Decompilation is nice C code. I don't want to look at a graph. I'm not a graph expert. So she took these CFGs, she went in reverse topological order, and she matched them to known patterns. For instance, if you have taken a program analysis class, you already know that this is the famous diamond structure, which is a classic indicator of an if statement. 1 node with 2 successors, and then a single successor that is a post dominator, both of them. Post dominator meaning it, dominates everything above it. There's no way to get through this control flow without going through that. So she takes these patterns, she matches them in reverse order, and then creates something that looks like C, which is awesome. Of course, at the end of this, it is still super duper ugly. We have a bunch of registers, we have a bunch of variables that are all over the place. So we need to perform optimization techniques to get rid of them, to condense them into maybe less variables, maybe less constants. In this example, I'm showing you a ternary, which comes out of this if statement because it aligns with the assembly, but that is not necessarily what Cifuentes did, because ternaries were a harder concept. You can consider this more along the lines of normal compiler optimizations. What are normal compiler optimizations? Well, that's actually a whole field in itself. I won't go into compiler optimizations because it is a lot, but you can consider decompilation and compilation tied together at the waist. They come one and one the same. So if you are going to do a decompiler, you need to use compiler techniques. For instance, this is the classic Dragon book. If you go to chapter 9 in the Dragon book, which is about optimizations, you will find very familiar techniques and code that are used in your favorite decompilers. So these techniques that she did were based on compiler techniques. And this is kind of this big first acknowledgement of we can make our decompilation look like the original source by doing compilation techniques again. So dead variable elimination, constant propagation, this general analysis of a language to make it simpler to understand. So that's how she did the optimizations. And then that structuring that I talked about a second ago, how she turned a CFG into actual linear statements, was about pattern matching. You take this pattern and then you convert it into what the C equivalent would be. And this is the very first kind of like naive way to take these condensed structures, make them into something more understandable. So what are these patterns, right? You need to know the patterns before you can do this matching. So from this dissertation, here is the patterns that are listed there, right? So we have composition, single branch conditionals, multi-exit loops. You guys may find some of these familiars. We have go-tos, we have endless loops. We even have switch statements, which is awesome. That's brilliant. And then, the classic diamond structure. So the key takeaway here is that the structuring that she did needed, a list of patterns that it could reverse match on the graph as it went backwards. So now that you kind of understand how this happened, how this began, it's very easy to transition into what the decompilation research areas are now, because they are finally rooted in what she did back then. And that's why, on Twitter, if you've seen her, she's considered the mother of decompilation. Super awesome, badass research, very cool stuff. So these are the research areas that I would consider the fundamental pillars of decompilation, or at least, some of these pieces. I've broken them into two different divisions. One is the fundamentals and one is the auxiliary techniques. The fundamentals you can consider are techniques that must be done to even have decompilation output to see anything. For instance, you're not going to be getting linear C if you don't first get a CFG, do control flow structuring, and then also variable recovery, because you need at least some variables. And then on top of that, on top of the fundamentals is kind of this newer, very, very new area of trying to improve other ideas, which are based on the original fundamentals. Things like symbol recovery, which is kind of making your decompiler look more like source in its symbols, like variable names, maybe even types, even function names, things like that. And then usability, which will be probably a lot of human studies that try to understand what a good decompiler even looks like. So now that you know about these six, or I should say 5 areas here, we will try to discover the fundamentals first and give you an up-to-date of what's going on here. And then we will go into the auxiliary techniques. So let's start with the very base foundational one, control flow graph recovery. Nothing else is possible without control flow graph recovery. So if you remember from the Cifuentes part, right, control flow graph recovery is taking this machine code that you have, lifting it to some form, and then getting this nice graph, which represents how you will traverse through the program. Now, this is different from a data dependency graph because it is representative of edges of control flow. So stuff like that jump not equals again. So there's really 4 phases that happen in CFG recovery. All of these have had recent research. So the first one is disassembling, which is hilariously what you would think would be the easiest part, which is just converting the opcodes directly into assembly lines. There's been trouble in this, and there's for various reasons, because you don't necessarily know where code starts and code ends. So there have been techniques to make this better. So first you disassemble. Next, you lift to an intermediate representation. This intermediate representation can have profound effects on the rest of your program, so it is a significant thing to mark here. And then the third thing you're kind of looking at, got a little glitch there for a second, is identifying function boundaries, and then fourth is resolving indirect control flow. So identifying function boundaries, right? Function boundaries are kind of these almost atoms of decompilation. It's maybe atom's a bad term. It's kind of the smallest big thing we work on. We don't want to work on a program just End to end, we decompile function by function, and then we see how they relate to each other. So identifying functions is an important piece of this puzzle. And then the fourth one is, of course, resolving indirect control flow. Indirect control flow is when you have taken this nice assembly, you've gotten yourself a graph, and you find there are nodes that have no out edges. If it has no out edges, it's either the end of the function or it is a indirect control flow jump. And that is bad, because when you don't have edges going to other nodes, you now will create disjoint graphs. And now a function graph may be split into two parts. So I've highlighted in red here, appropriately, the hot areas, the areas that I think are the most on fire, making some of the biggest changes in decompilation. Resolving indirect control flow. Over here, I have these two citations from Usenix in 2022 and NDSS in 2021, which is about trying to see, one, how accurate are we actually getting control flow done? And then second, how can we refine indirect calls more accurately? If you are familiar with anything to do with static analysis, this requires a lot of hard techniques like Anderson pointer analysis, reaching definitions. It's slow, it's painful, and it's hard to do. You need a whole pipeline to do it. Disassembling, this is another one, a recent paper, data log disassembly. This was in 2020. This had some profound effects on the way it can, get you these instruction layouts and how accurate it is. So like I said, there are problems measuring accuracy of your CFG and also, resolving indirect jumps, because there's still a lot to resolve. And this is an open problem. So there's a lot of area for movement in this kind of topic. So the next one is type inferencing and variable recovery. So after you have this nice control flow graph, you're probably wondering, how do I get rid of the registers? How do I get rid of my stack variables? That is a good question. And there is a lot of work that goes into doing that, right? So you need to take something like this reference here, RVP minus OX4, which is a memory location. And you need to recognize that that memory location is not only a storage location, but also has a specific size. And this size may be hard to determine, because remember, when you have things on the stack, everything is right next to each other. How do you know the difference between a variable and an array? Lots of techniques to try and figure that out. So there's some approaches, right? We have dependency analysis. You can try and see, how is the variable used? How is it accessed? How do people touch it? This kind of gives you insights into maybe what the size is, and that size gives you insights into what the type is. Another one you might be doing is some storage location analysis, which is related to the dependency analysis. And then the other one is some just good old fashioned machine learning. And if you're not bringing machine learning into a field, this is your chance. So machine learning is another way. Again, here's some of those recent citations from papers. The 2011 paper is rather old, but it at least gives you some introduction into how people did this type recovery, because you'll find these same techniques described in TIE, which is the 7th citation here. You'll find it embedded in IDA and Hydra and all these different decompilers. And then the 9th one, machine learning, is a very recent paper about getting variable names and types from machine learning based on, training on a bunch of normal source code and decompilation and seeing how these things map. So there's a lot of room for growth still, because if you've ever used IDA, you know that types are often wrong and structs almost never exist. Lastly, of these fundamentals, and my favorite topic, if this is my research area, is control flow structuring. So control flow structuring was that cool part we talked about earlier, where you take some patterns, you take this graph, and finally, after doing all these other analysis, you condense them into these nodes of code, or code nodes. So there is a lot of different approaches to structuring. I really shouldn't say a lot of, there's very few, but there is a good amount of papers that try to analyze how this happened. So you have pattern matching and semantic preservation. So pattern matching is exactly like the Cifuentes one we talked about, where you just have patterns, you have your list, you go up the graph, and you match pattern to pattern, trying to get yourself some nice decompilation. Phoenix is a paper that introduced semantic preservation, where, hey, we know pattern matching may not always be good enough. Maybe you need to read the conditions to be able to understand how to structure things correctly, how to get the correct patterns. The next one is a fundamentally different approach from both Cifuentes and from Phoenix, which is about region-based analysis, where it says, instead of trying to match patterns, why don't we try to understand the atoms of this graph, the smallest units, which we'll call regions. And then we try to understand how conditions touch every single region. This has an interesting effect, which will become much more important later in this talk, which is it has no go-tos. And that will become a very, very big point of discussion and trouble in decompilation, is that there are no go-tos in Dream's output. And lastly is a newer paper called RevNG. It was in a second-tier conference for security people, and it is about doing the same thing that Dream did, but then adding one more extra step, which is about block duplication, where you see some patterns after you've done this fundamentally different approach, and you try to fix them up to be more correct. And you can do that with block duplication. So as far as new structuring algorithms go, or different approaches to structuring, there are only two fundamentally different approaches. And that is Phoenix, or also Cifuentes, because I'd say they're near the same thing. And then you have no more go-tos, also known as Dream. So these are the two big clashers of structuring, and that's all. Those are the only structuring algorithms that exist. RevNG is just an extension of Dream, so I would argue that it isn't novel enough to indicate a new structuring algorithm. So I want to highlight here the years at which these came out. So 2013 is when Phoenix came out, and 2015 is when Dream came out. So if you're considering this 2020 paper not a fundamentally different one, that means we haven't had a new structuring algorithm in over 7 years. If you're any person in academia, a 7-year drop, you may consider either this field is dead or this field is solved. I've talked to both parties where they think decompilation is dead, there's no way to move it, and decompilation is solved, why move it at all, we're done, right? I hope that by the end of this talk, you are not in either of those parties and you realize there's still a lot of room for at least structuring to continue to move. So why do I think structuring is so important to talk about? Well, one is my bias. I love structuring algorithms. That's my research area. But also because it has a very big impact on readability. I'd say an even bigger impact than variable names. So here on the left, I have a classic super simple C program that I am almost confident everyone in this Zoom chat has written before. This is a simple Boolean check. It does a OR on A and B, which if you are knowledgeable about C, actually does a short circuit evaluation. If you don't know what it is, you can actually tell what it is from the graph. Basically, if A is true, you don't even evaluate to see if B is true. You just skip it altogether and jump right to the true condition, which is foo in this case. So this is fun. I wonder what people think this will look like when you have a naive structuring algorithm that just tries to structure it. I would hope that it would look something like this, maybe nested, because I know that Ghidra looks bad with nested ifs. However, it actually will likely look like this. You can see why this kind of happens if you look closely at the graph. The B condition got its own if, and the A condition got its own if, and then we have else bar here. To give you, again, some kind of intuition onto how this happens, so that maybe when you look at your decompiler nowadays, you can understand why. It goes backwards in the graph, right? So we would start at these first 4 blocks, and we'd say, hey, I recognize this. This is a classic diamond, so it's an if statement, right? All right, that's easy. If B, foo, else bar. Simple to go. But now we get to this other guy, and we go, wait a second. 2 of these blocks we already structured. We can't structure them again. We've already identified them as a different structure. And this structure is a single case if statement. So what do? Phoenix coined this term virtualization, where we take one of these edges and we say, forget about it. Let's just cut it. Let's make it a go-to. And so now you get this go-to, right? You have the if statement at the top, which will go to B, and it simulates this short circuit evaluation. I hope from this, you can at least see that structuring, or the algorithm, the order, and how often you do it has a significant impact on the exact same code. If you were to compile both of these codes, they will get you the same thing, but they look completely different and they're much harder to analyze. So the last research area is this auxiliary research area, which is about symbol recovery and usability. There are a lot of cool works that are happening right now in this area. Lots of them are user studies, which try to look at reverse engineering, but may not necessarily look at decompilation. So you have people trying to understand how decompilation techniques happen from the same people that made Dream. They have Dream++, which analyze that. You have better information displaying the same thing. You have people trying to understand how others decompile, like the order at which they would do things to decompile, like in Decomperson, or how well they decompile, I should really say. And then you have nice symbol recovery things like variable names and function summarization, which have mostly been spanned around machine learning right now. So I think this is a great time to take a short break, to take a pause for a second and go through any questions. Recall we had these many different topics. If you guys have any questions, now is the time to throw it in the chat, or to unmute yourself and ask. You can ask anything about these areas before we move on to the actual, second half of this, which is how they're applied in normal decompilers. So does anybody have any questions? Oh, awesome, I see one. Can you throw, oh, yeah, I can throw the tiny URL in the chat, which will be a fun zoom right back to the beginning. Yeah, there you go. That is the URL to the slides for anybody that wants to look at the slides more specifically. Although I would say you probably only want to start looking at these citations after the talk, because all of these projects are very dense. So they are much harder than the average paper. I hope at least from this talk so far, you're starting to understand that decompilation really has a lot of pillars that build up together to get this final complex thing you have. A lot of it is engineering work. Anybody have any other questions about any of these approaches? You can even ask about machine learning if you're a machine learning savant and you would like to know about that. All right, I'll give it another second unless you're typing something very long, but I think we'll move on to the second half of this talk, which is now about how these things were applied in decompilers you find in the real world and the academic ones that we talked about. All right, so modern decompilers, right? This is the third section of the talk, which is about all these different decompilers. I'm actually missing revng here, but that's okay. We'll consider it kind of off the bar for now because it didn't have a fundamentally different technique. So we have all these different decompilers. Maybe you recognize some, maybe you don't. One you really may not recognize is Reco. Reco is an open source decompiler. You guys can search it up if you want. I list it here because if you are interested in decompilation, I find it a very good decompiler to look at. It has code that is easy to understand. It's very approachable, unlike Ghidra, which is super nested. You got all these Java interactions with C code, Slay, it's nuts. Reco, much simpler, straightforward. Very good if you're trying to learn. So for our talk about modern decompilers, let's kind of sparse some of these out a little bit. So I wanted to emphasize the bottom here, right? Dream, which is the decompiler I talked about that had no go-tos. It's not open source, or sorry, my bad. It's open source, but it's Windows XP only, which is really hard to use if you try to use it for anything more than one binary, or any binary that's more modern. Windows XP is pain. So you can consider Dream very bit rotted, although the approach is very good. You have not a lot of code that you can actually use, so it's hard to extend this. Phoenix as well is just not available. You can't find it online. You can't find a closed source, so you can't even get access to Phoenix. So if you're trying to even understand how Phoenix works, like a programmer, you want to debug it, you can't. So we cross these out and we actually bring in our own decompiler. This is one of the things I work on as part of my PhD, which is Anger. Anger is a symbolic execution engine, but it's also a decompiler. We have a decompiler built in. And part of that decompiler re-implements Phoenix and Dream. You can use them separately to understand them. I have to at least note that the Phoenix implementation is not exact. We tried to get as close as we could, but we had to make some fixes because some things just don't work for scalability wise. We also have IDA Pro here, which is different from Binary Ninja because it's expensive, but it is also much better. or at least better enough that it doesn't make a difference to list this as part of our decompilers. And then we have Ghidra, which is the best open source kind of approach. If you're any newcomer to decompilation, you've definitely heard of Ghidra because it is the one all the people on YouTube use, everyone tries to use. It's very popular, I'd say. And after the release from the NSA, I think a lot more people know what decompilation is, or at least that it's possible. So let's step into some of these decompilers. The first one is Dream, again, re-implemented on Anger. We will be looking at all of these modern decompilers with a focus on the control flow structuring algorithm, because I think that is the most impactful thing that you'll see for readability. And as you might have already been starting to insinuate here, some of the crazy stuff you see in your decompiler is because of bad control flow structuring choices. There is a choice that exists that will make it look the best. So region identification inside of Dream, fundamentally different from everybody else. They do condition guarding based on pattern match, or sorry, condition guarding based on region identification. So region identification is taking these blocks, right? These blocks and finding if they have a single entry, single exit. So for instance, foo and bar here, you could actually collapse them into one guy and they would still have a single entry and a single exit. In this case, the region actually gets a little broken because of that other entry, but it's okay, you can still condense these into one. The idea is you condense all of these regions into one node and you ask what conditions will touch this block. So you're actually not even matching patterns at this stage. You're just seeing, hey, does A need to be true for me to get to foo bar? Does B need to be true to get to foo bar? If that's true, let's just put that in the if statement. So this is kind of why it removes go-tos, because you could remove every single go-to edge by instead just introducing a new if statement, because you know the conditions and you're a Dream. So you just put an if statement there to block off any control flow that would have got there otherwise. Phoenix, I feel you guys are very familiar with now. Phoenix is just a classic pattern matching. It has no knowledge of regions. So it doesn't do any of that region stuff I said, it just pattern matches, right? You have your list of patterns, you go reverse on the graph, you find things that look like C structures. So this is very close to Cifuentes. So these are kind of the two different ways we do structuring. Now, with that in mind, how is IDA and Ghidra so much better than Phoenix, or at least we're assuming they're going to be? So IDA does pattern matching too, but we can only get so much knowledge because of course it's closed source. Again, one of the problems of decompilation as a field is that so much knowledge is locked behind doors. You can actually find a lot of information of the choices they made, why they do them, because this field is both so powerful and so you can make a lot of money off of it. IDA Pro is like $6,000 a year for a single license. So, maybe make a new decompiler and make a lot of money. With they do this pattern matching with no knowledge of regions too, but they have some kind of extended pattern knowledge. So they knew more patterns than Phoenix did, or at least they identified new ones from compilers. And so they have more structures they support than Phoenix does, which you'll see results in a more structured code. In addition to that, Hexrays also has some signature matching. It tries to do symbol recovery in their Lumina server. They have some integration with dynamic analysis, and they also have a very, very highly optimized variable and definition use. Their constant propagation is just very good. They get it right almost every time. So the big difference then between Phoenix and IDA Pro will likely be these extra heuristics that they found, like extra statements they found for ternary operators, understanding how to structure ternaries better, some little heuristics that they've figured out over time by having many binaries. Ghidra is a lot of the same thing. Ghidra does not take the Dream approach, and neither does IDA. Both of these avoid Dream, and they go for more of the Phoenix idea, where you do pattern matching again. Don't need regions, you just go up the graph with patterns. And you extend this pattern knowledge with some semantics you found with lots of test cases, lots of stuff like that. So you can consider, because of IDA and Ghidra's existence, which are almost a decade old, Ghidra actually could be way older than a decade. I have no idea how old Ghidra is because it was released by the NSA. We don't know how much time was in development or what test cases they used to actually make this decompiler. But you can consider them testing this kind of structurability. And of course, they have integration, dynamic analysis, and symbol recovery. So the gist here of these different decompilers is all of them which are used by us modern people, by us reverse engineers, whether you're using IDA, Ghidra, and this even occurs for Binary Ninja. You are using this Phoenix algorithm or this algorithm of pattern matching going backwards, because for some reason, people don't want Dream. I wonder why. So who is the best then, right? You came here for hard answers. You want to know which decompiler should I be using, and if I can get rid of my $5,000 IDA license. Well, maybe not, because the question is not so easy to answer. Previous ways to measure the quality of decompilation are fairly complicated because we don't have any good way to measure how good source code is. So we don't really have a good way to measure how good decompilation is. And I find that these problems are fundamentally different. So for instance, one way people did it in Phoenix, RevNG, and Dream is to just straight up count go-tos, because we all acknowledge that go-tos are bad, or at least, too many go-tos are bad. If you've seen Dijkstra's, acknowledgement, go-tos considered harmful, right? These are things that we want to avoid, go-tos in source code. So you just count the go-tos. Whoever has less go-tos is the best decompilation. Maybe. Phoenix explored the idea of recompilability, that the time decompilation is most useful is when you can recompile it. I tend to differ because, human-centric decompilation doesn't necessarily care if you can recompile it. Bug Hunter doesn't care if you can recompile the binary. He just wants to find the bug. Another one is number of lines. This is what Dream did. They did this in a more complicated way than just counting lines. They tried to count the number of statements. Cyclomatic complexity, which is an extension of some source code analysis things we did. You can consider it. This is kind of an estimation of what it is without showing you the real algorithm. It is the number of linear paths through the program. So you just try to count how many linear paths occur. Whoever has the lowest or the one closest to source is the winner. Now, none of these ideas have been tested against humans. We don't actually know which one humans consider the most impactful. We were kind of just guessing, and we do these based on piggybacking on software engineering stuff. So let's look at a very specific use of decompilation on a binary called format from core utils. Now, I'll go out on a disclaimer and say already that this binary format should have already been tested on all of these decompilers. Core utils is mentioned in every single structuring paper from Phoenix till now. They use the same binaries. So these binaries are the ones that they have already tested on significantly. You can consider if IDA and Ghidra have a test case backend, right? They're testing on this binary. So you would hope it's good, hopefully. So on the left, we have the source code. The source code may be a little dense, and I'll try to explain it. I'll leave these up as we try to explain what's going on. So I'll just put up everything, and then we'll kind of look at it closer. So we have source code, we have IDA Pro, and then we have Ghidra. So we'll just allow these to sit for a second. On the left-hand side, we have ternary operators inside of an if condition. It's the last if condition where they're checking to see if something is, %s, or erroring, I should say. And so they have a ternary operator which will change what happens. You can either have this one argument for error or no argument for error, something like that. So if this were to be expanded as a normal condition, it would be if this thing, else this thing. So just like a normal if statement. Now in IDA Pro, you'll notice that something completely different happened. They decided to connect this second place with a go-to. So let's actually highlight these very important places. So this DC get text, right, which is inside the ternary operator, they decided that this would actually be the best if we connected it with a go-to based on the order at which they traverse patterns. So you have this first quote arg going to the second quote arg successor. I know that might be confusing because the source code only has one call quote arg. So there's a lot of content on one location. So the gist I'll try to get to is a go-to exists in IDA Pro, but a go-to does not exist in Ghidra. There are no go-tos in Ghidra. And the reason there are no go-tos is because Ghidra decided, hey, let's not virtualize this edge. Let's instead bound it with a condition. So that's what they did on Ghidra's side. They do this if I_var2 does not equal 0, and they bound it in the condition. But in IDA, we say, hey, condition is bad, let's just jump there. So now you have two different ways to represent the same program, which are both very different from what you would expect to see from the source code, especially because there are two calls to quote arg, but I won't get into that. That will be some future research that maybe you can find when we publish it. So these are the best in class, and they're still kind of far from it. And it's because of the structuring choices they made. Now, I'll also show you the academic version. You'll notice that the academic version for Phoenix also has a goto, and Dream, of course, has no gotos. So this gives you that much, better confidence that IDA and Ghidra are basing their implementations on Phoenix, which also shows this goto. However, whatever Ghidra did, they didn't do Dream, but they decided that instead of connecting with a goto, they might just use another if condition. So that is a heuristic that made their structuring algorithm better. It's not necessarily part of their native structuring algorithm, unless they published on it, which they have not published on it. So I'll give you a kind of bigger view of this. You looked at one binary for a second, and I tried to show you how these gotos have a significant effect on the readability. But what exactly is it like across all of the binaries in core utils, or a bunch? So here's a graph of gotos I have measured for you for all the binaries inside of core utils. We uniquify the functions so that every function is only analyzed once. So this kind of demonstrates the biggest problem with IDA right now. Look at IDA. It has the lowest gotos of all the decompilers here that are not Dream. Now look at source. There's 87. So somehow we only had 87 gotos in the original source code, and those turned into 1,700 gotos in IDA Pro. This is an insane jump, right? This is massive. The jump is so big that it makes you wonder, are they missing something fundamental in their structuring algorithm? Maybe. I think it's at least worth considering how our decompilers are going wrong by looking at these structuring algorithms and comparing them against each other here. You'll also notice that IDA isn't actually that much better than Ghidra and goto counts. You would be thinking, this is thousands of dollars have been invested in IDA Pro. This should be way better than Ghidra. But this kind of shows you the limits of the structuring algorithm base that both of them are using, which is, again, this Phoenix pattern matching base, which doesn't work on regions. And lastly is, of course, Phoenix, just to show you what Phoenix looks like. And it makes sense, because if these two things are based on Phoenix, they should be better than Phoenix because they've existed longer. And they are better. So that kind of adds up. Now, you're definitely noticing the Dream, the far last thing on this graph. It has 0 gotos, which would indicate that it is the best decompilation. But is it actually the best decompilation? Right? So Dream is also called no more gotos, but I like to refer to it as no more gotos, too many conditions. Look at the last statement here, which is about the error and the TC get text. You'll notice that the last statement on Dream has this huge if condition. If v3 doesn't equal 0, or v6 equals 0, and v4 doesn't equal 0. And you'll notice that they're overlapping between that statement and the last statement. There's a bunch of conditions. So there's so many conditions, and that's how they got rid of the goto. They replaced it with the conditions that were inside of the graph. And that shows you, again, that this structuring algorithm has a huge change on what can happen for this actual condition output. So the reason nobody has adopted Dream inside of IDA, inside of Ghidra, even though we've considered to solve structuring, is because they create this bad trade-off where instead of having gotos, you now have an insane amount of conditions. Now, you may be thinking, all right, Zion, you showed us one example, who cares? If there's only 87 gotos in the source, this is only going to happen 87 times. It's not that bad. Well, it's pretty bad. So this is Boolean operators, right? So this is on those 87, on the same amount of functions that we had for the goto counts. This counts how many Boolean operators are present in the decompilation. Now, if you see Dream, you'll notice that it is 9 times larger than what it was in the source. So this indicates to you that you have an insane amount of if statements, conditions, guarding blocks that make your decompilation way harder to understand than just having go-tos. Now you have to decide, do I want 9,000 conditions or do I want 1,000 go-to statements? And I think neither of them are correct. Neither of these approaches actually get you the right thing. And this kind of illustrates why no one uses Dream in the real world. It's because of these conditions. So is anybody win if there's all these go-tos and Dream doesn't work because it gives you no go-tos, but then it just trades it off for a bunch of conditions? Is anybody really better? And again, that's still a hard question to answer. You can look at that last metric I talked about, which was cyclomatic complexity by RevNG, right? And you'll notice that for Phoenix, Ghidra, and IDA Pro, they are very close to each other in cyclomatic complexity. The one that actually has the lowest score that is closest to source is Ghidra, which is surprising because most people would say IDA displays better decompilation than Ghidra does. So there is either two things happening here. Either Ghidra is better than IDA, which I doubt, or this cyclomatic complexity isn't actually a good metric. And I will argue that it isn't a good metric. If you're interested in this more, you can talk to me offline about it, but it has some interesting things to do with go-tos. So the last part of this talk, which will be very fast, is the future areas of research. Things that you could do if you were looking to get involved in decompilation, where I think the field is moving, and kind of some cool topics that are coming out, right? So the first one, very connected to the thing we just talked about, is evaluating decompilation quality. How close is decompilation to source? Nobody has the answer. Is quality based on closeness? Is decompilation better if you're closer to source? Can we use source code metrics like cyclomatic code complexity? Is that allowed? Do these things even translate when you use decompilation? These questions have yet to be answered. Oh, and then of course this last one, understanding how humans perceive the difficulty of decompilation, because we don't actually know what parts humans think are the hardest, aside from the one study by Dream++, which explored their reversing techniques, right? We have other problems too in this fundamental base of decompilation, which is control flow structuring. What is the middle ground between IDA and Dream, where you can have some go-tos, but not too many go-tos? In the ideal world, you have the exact amount of go-tos that source did. Yet IDA is so insanely far off and Dream is so insanely far off. What is the middle ground? And does a new structuring algorithm exist that actually answers this? And if you have these same questions that I do, I think a nice place for you to go mess around with it is, again, our decompiler. We have our decompiler anchor management, where you can go mess with the structuring algorithms and see what things have changes if you're interested in this. And then the last one is, why are there still go-tos in decompilation? No one has answered this. Two last topics. We have CFG recovery, which is how do we deal with the abstraction like classes, which is, again, has to do with indirect jumps. How do we make indirect jumps work when we have classes that may have virtual things? How inaccurate is our indirect jump resolution currently? We don't have a research study which answers any of these questions. And the more inaccurate your CFG is, the more inaccurate your decompilation is. And lastly is usability. We have a lot of ways that decompilers can become better from this quality standard. How do real reversers actually use our decompilers, right? Like, do they use it fundamentally different from how I would, because I'm a researcher in decompilation? I don't know, because there hasn't been enough, quantity metric or qualitative metrics and quantitative metrics that show us how humans actually use decompilers. Another one on that is dynamic analysis, right? Do people actually benefit from having dynamic analysis in conjunction with their decompiler? One project I did here, which is open source, is called Decomp to Debug. I did a talk on it earlier this year, which is about making dynamic analysis possible in your decompiler and sharing symbolic information. This is another idea of pushing how we use decompilers into a more user-friendly standard. Human collaboration is another project I worked on. How can we make humans interact with each other better? There has still been no studies to understand how humans interact with each other on decompilation, or how that might actually improve the decompilation experience. And then, of course, if you're any human that has existed for the last 6 months, you know that we got to get AI in there. How can AI help us? Luckily, I have answered some of those questions for you, so you don't have to agonize over it. I have made something called Dyla. You can go and check it out. Again, these are all the GitHub links for them. Dyla is function summarization and identification. So you can test it on your decompiler. It doesn't matter which one you have, IDA, Ghidra, Binja. It's supported on all of them. So just to kind of dig into that AI one quickly, because it's such a hot topic, I had to at least add an extra slide on it. Right, there's variable name recovery, which we've already talked about. There's types, there's structuring, maybe, that hasn't been done yet. And there's summarization, maybe. There's been no formal study to understand how well AI can summarize decompilation, or if humans are not even needed in this decompilation loop anymore, if summarization has just beat humans out altogether. So on that note, this is kind of the gist of everything we have. Again, I've given you some questions to understand how decompilation can be moved with our new future topics, what has gone on in the past, and kind of, these fundamental techniques that make up things you see in the real world. And on that note, I'd like to open it to any questions. Again, any questions you guys have on any of these topics is fine. I'm open to answering, opinions if you're curious which decompiler is the best. Any idea what method the decompiler in Hopper disassembler uses? Yes, I believe Hopper also uses the Phoenix method. Hopper does emit gotos. So the really easy check for this, if you're trying to find out, hey, what does the decompiler use, but I'm not really good at reading source or it's closed source, just look for gotos. If you find gotos connecting two statements, that means it is likely a Phoenix implementation. And colloquially, again, Phoenix would be this pattern matching versus condition constraining. So different approaches. No problem.
I'd like to ask a question real quick.
Yeah.
So how useful could decompilation be in the context of like reverse engineering? And what I mean by that is I'm kind of in the HPC and systems background, and something that's happening that I think many of us in computer science are aware of is, Dennard scaling and Moore's law is slowed down or is ended, and now we're kind of seeing this idea is like, oh, well, now we have to kind of rethink how we do computation from like a hardware. Right. And so in my mind, I'm thinking, oh, well, now we're going to see a lot of different accelerators, different types of devices. And many of these devices might end up being proprietary. And so that might take control out of, the academics' hands and put it more into industry's hands. And so, I guess in my mind, it would be nice if you had this accelerator and you didn't want to be bound by the limitations of whatever the vendor decided was, the driver for that device on a systems level.
Yeah. Yeah. So is your question kind of along the lines of how does decompilation address this?
Yeah, like how can, I guess, like, the question is like, is decompilation useful in that reverse engineering? Like, if you were interested, you were like, hey, I don't want to be limited by what NVIDIA says, how I like poke the bits on the GPU. If I wanted to make my own open source driver or something,
yeah,
is it useful in that context, or is it better to just kind of see how it lights up and reverse engineer on a higher level, is kind of my thought.
I think decompilation is this key to understanding all of the devices in the world. I think you're right. We're in kind of a pivotal moment of deciding whether things are going to stay open source or if we're going to go full Monty into closed source. And decompilation is really your biggest technique for, one, staying out of the 90s. So you're not staring at assembly anymore, right? Because that's how everybody did it before. They just stare at assembly to understand your own computer. Decompilation gives you that ability to own your devices, to actually own them. No one would ever question you for fixing your own car. So why do people question you for trying to fix your own software or hardware, right? It's madness. You can go buy a manual for your car. You can go and find a technician who'll do it. But if you try to go find a guy to fix your software, you're going to be, finding some sketchy guy on the dark web like, yeah, I'll patch your software for you. So So decompilation is really, this is the empowerment for the people, I'd say, for the bigger community, for the curious. If I were to rename this talk, it would kind of be along the lines of, the future of democracy for reverse engineering, because this academic approach where we open source our decompilers makes it easier for all of us to reverse engineer together. So I'd say, yeah, it's pivotal. It's pivotal.
So and then I guess as a follow-up question, are there unique challenges when decompiling that's kind of something that's more of an application versus this is like a system level driver or something in the Linux kernel or?
Yep. The biggest problems are along two lines. The first one is blobs. When you have firmware, you may not necessarily have a file, like a nice compact file, like an ELF, a PE, or a Mako, right? You just get a blob. You just get binary data in just some thing. And when you don't actually know the entry points, functions start, data starts, decompilation becomes super duper hard because you don't even know where to start converting graphs into structuring. So firmware makes it really hard when they come in these blob formats. And secondly, you may be doing something in your C code which directly touches hardware, like flipping, bits on IO port. And if it's not just like an abstract function, this can look crazy in decompilation, especially for stuff like ROM where you're accessing specific memory locations, right? It'll just be hard coded and it'll just look like nonsense in decompilation. So the future of that will really be trying to decipher these things from the mass amount of products we have. As much as I hate to say it, it'll probably come from machine learning to be able to identify when you're actually looking at firmware and when you're looking at normal code.
All right. Yeah, thank you very much.
Awesome. I see one other one, fundamentals were really interesting. Yeah, no problem. I think they are also very interesting. If you guys ever want to talk more about this, you can find me on Twitter. Like I said, you can also email me. It's on my my site. You can find that. So yeah, I love to talk about decompilation. I think it's a great topic.
Has any of the research focused on attempting to break the decompilers?
Yes, there has been research that is focused on it. Maybe I can link this. I won't be able to link it now. If you search up RET2 systems, the dangers of decompilers, there is some introductory stuff about how you can really mess with decompilers. If you're a decompiler, all of us are kind of assuming you're using sane code, that you're trying to decompile something that is okay with being decompiled. And we all know that that's not the case. As we progress into the future, maybe NVIDIA will introduce things into their code that tries to stop decompilation. An example of that is non-returning functions like exit. You can disguise your functions to look like common functions in libraries, which will cause the decompiler to make assumptions about what code is reachable, just like a compiler actually. And using those techniques, you can completely cut off the decompiler from even showing you code. And the analyst doesn't even know.
There's a lot of anti-forensic techniques that are trying to do some of this, and I've looked at some malware samples that are intentionally. So I just wondered how much of the research, but I'll take a look at that one. Thank you.
Luckily so far, because decompilation is, I don't want to say in its infancy because it has existed for this long, but because decompilation is still so bad, no one has even tried to really fight it like on a massive scale, like malware actors. They fight the disassembler, right? They'll say, forget it. This guy, he owns IDA Pro. He's probably good already. Let's just pack the binary so that it's not static. And then let's just throw in anti, debugging. So you can't break there, or it tries to kick you out of the program, or forks, right? So they don't even really mess with these decompilers yet, because one, very few people on the whole internet understand how they work internally. And two, they're not widespread enough and good enough that people care. Yeah.
I can ask another one.
And then you get into VM obfuscation, which was the topic of my class this Wednesday.
Yeah, of course. You have VM obfuscation, which at least is a little easier to understand when you have a decompiler, because now you can see, usually they look the same from the beginning, but then what it unpacks God help you.
What do the decompilers do when they run into inline assembly?
What do decompilers do when they run into inline assembly? So this is a research area that also is currently in the works. Some people are exploring this. Currently, some decompilers have some heuristics to know classic inline stuff. You can divide these into two different topics of inlining. So there's inlining for built-ins, which are stuff you would expect from like Windows or from Linux. You know them. One example is string compare. If you're string comparing for only one variable, they're not going to call string compare. They're going to put your variable equals the character. They're just going to get rid of it. They can do that for up to 15 characters or more, right? And that's just one built-in. The other category is functions user rights, which gets inlined. So the first category of built-ins, those ones are actually pretty well solved by things like IDA. IDA's pretty good at identifying when you're using a built-in. This other area of knowing when a user function has been inlined, that one is still very fresh and really doesn't have any good solutions at all. Because to be able to understand when a function has been inlined, you need to understand when two sections of code are semantically equivalent, which there is no approach to do that. So there is no way right now to be able to even do it. But I think in the future, next 1 to 5 years, I think we will find a solution that comes strikingly close.
Thank you.
Any other questions from the group? If not, let me thank you, Zion, for this talk. Excellent kind of roadmap of this entire area, and also very relevant talk because even in security, I think a lot of people aren't as familiar with decompilation as perhaps they wished. And I'll definitely be sharing this with current and future students because, yeah, you did a really good job of laying out the field and the history and where things are going. So thank you for that.
And definitely on my part, it's me, begging to the universe of academics, please bring me some colleagues to work with. It's so lonely. Bring more people to decompilation.
And it speaks to me also the social empowerment angle that you touched on in the end there. I'm sure Richard Stallman would smile at your efforts. So
thank you.
So with that, thank you everyone for attending. I believe this is our last talk before spring break. Things will spin back up once we come back. And I think that's all the housekeeping that I have. So thank you all for attending, and I'll see you on the next one.
Thanks so much.
Carter, if we want to bug someone about the recording of this, are you the person to bug? Or will it be posted?
Yes. Okay. So if you know the ICDT website where the event information is, we are slowly but steadily taking these recordings and with the presenter's permission, making them publicly available there.
Okay, cool. Thank you.
So if you know where that is, that's where it is. If you don't know, just shoot me an email or something and I'll send you a link.
Okay, thank you very much. And thank you, Zion.
No
My pleasure.
Thank you, guys.
Yeah.
All right. Thank you for having me. I'll see you.
Yep. Take care, everyone.